So before we do that, let's quickly recap what we looked at previously about point estimates. So an estimate of a population parameter given by a single number is called a point estimate for that parameter. Examples of this have been, we had x bar for mu, we had s squared for sigma squared, and we had s for sigma. In these cases, these are our point estimates. They are just a single value which describes some parameter for our population. Now, with this, we're going to have what's called the margin of error. So the margin of error is just how far our point estimate is away from our actual parameter. So an example of this might be, let's say that we have data that comes from a normal distribution, which is centered on the mean mu. So there's some parameter mu that exists, but we don't know what that is because we don't have population data. What we have instead is we have a sample and we get some point estimate for that right here. So our margin of error is just the distance from our point estimate to the actual parameter. And the actual formula for this is as so. So our margin of error, so we'll just call it E for error, is going to be the absolute value of theta hat minus theta. Where theta hat, if you remember, hat just means the statistic or point estimate for that parameter. So if theta is our parameter of interest, theta hat is our point estimate for that parameter. So for example, if we were doing it in this case, looking at the margin of error for the mean from our sample to the population mean, this would just be the absolute value of the value that we got for x bar minus the true value mu, and then we take the absolute value of that because all we want is we want the magnitude. How far off are we from the true value, not necessarily what direction is it facing. Now, this may raise some questions. You might be thinking, well, how do I know what mu is? And that's actually a really good question because if I already knew what mu was, why would I be taking a sample, right? If I have population data, so I know the true mean, there's very little reason for me to ever take a sample to get a point estimate to then try to estimate what that true mean is. So I want you to kind of think of this as the idea behind error. There exists some true mean mu that for our population data. We don't know what it is, but we do know that there is some amount of error from our sample statistic, our point estimate, that we get to represent that parameter and the true parameter. So there's some amount of error, but we don't know exactly what it is. Now, later on, we actually will look at a way to kind of use an estimate for what it could be. But I just want you to be having this in mind while we're trying to figure out what this mean mu of this normal distribution is. So now what we're going to do is we're going to start looking at another way that we can try to estimate what this mean mu is other than point estimates. And we're going to first be looking at the confidence interval for mean mu when sigma is known. So in this case, we are going to assume that we do know what sigma is. So we have a simple random sample of size n drawn from this population, and this population's standard deviation is known. So we have sigma is known. And if our x distribution is normal, then our methods will work for any sample size n. Now, what does this mean by if our distribution is normal? Well, this is where we're going to start by looking first at our assumptions. Can we assume that we have normal data? And there's going to be two assumptions that we're going to be using. The first is, do we have a large enough sample size? So this would be, for this class, is n greater than or equal to 30. And we discussed previously why this is. This is using the central limit theorem. If I have normal looking data and I have at least 30 sample size, then I can assume that my data will follow a normal distribution. Now, realistically, in the real world, you're probably going to need a larger n than this because you're never going to have perfectly symmetric bell-shaped data. So the more skew you have, the more it deviates from looking like a perfect bell-shaped normal curve, the bigger your sample size would be. In fact, later on, we'll actually look at how we can calculate minimum sample size, assuming from a normal distribution. The other thing that we could have be true is if sigma is known. Now, both of these are from our central limit theorem. The first states, which is actually this one, sigma's known. If I have a known normal distribution, then any distribution of samples that I take from that normal distribution will also be normally distributed. So that's this statement here. And then it said, even if I do not have a normal distribution, or I do not know it's a normal distribution, given a large enough sample, then I can also say that it is normally distributed. So these are going to be the assumptions that we are going to check to determine whether we can use this method. Now, one last thing I want to talk about with this is that this or this needs to be true. So this is an or statement. Now, if you remember from probability, or means that I can use the method that we're going to talk about if sigma's known, or if n is greater than or equal to 30, or if both are true. The only time that I would have to use a different method is if both of these fail. So the fact is, this is an or statement, so only one of these or both can be true. The only way that it's going to fail my assumptions is if both are false. So now let's actually talk about what a confidence interval actually is. So a confidence level C is any value between 0 and 1, that is to say 0 to 100%, that corresponds to the area under a standard normal curve between two values, negative ZC, which we'll call Z critical, and ZC for Z critical. So pretty much what this means is this. Let's say that we have a normal distribution. We know that the area under this curve is 1, and we're going to have some probability. So this is a standard normal. And we know that we can have some probability based on the interval between 0 and 1. That's basically what the first part means, is that I could have a probability of 0, meaning that I have like the probability of a single point. But what we're looking at, though, is we're saying if I have some negative Z critical and some positive Z critical, this is going to give me some amount of the data that I can be confident that my data point falls between. And this is because based on our, basically think of it like your empirical rule, right? We had one standard deviation was 6 to 8% of our data, 2 standard deviations was 95%, 3 standard deviations, 99.7%. Now what we're saying is, well, I can do that for any interval on a standard normal distribution, right? If I have some Z and I go out the same amount to the left and right, I can account for any amount of data from that standard normal distribution. And that's going to be C, which stands for my confidence. Now, the three most commonly used confidences are going to be C equals 0.9, C equals 0.95, and C equals 0.99. So now let's actually talk about how do we find this using our table. Well, first, let's start with one of these cases that we're looking at here, and we'll figure out what Z values would cause this to be true. So let's start with the fact that I have my standard normal, and I'm telling you that between negative Z and positive Z, I want there to be, let's say, 0.9 of the data. So I want to be 90% confident that my value will fall in here, right? Because if this distribution represents all the possibilities, and we know from a normal distribution that if I go out this amount, that 90% of the data will fall within this interval. So 45% will fall on this side, 45% will fall on this side. How do I determine what these Z values are? Well, for our table, because we're using a table that specifically has positive values looking to the left, we're going to figure out what is this positive Z value that makes this true. So I need the positive Z value where 90% of the data is to the left of it to here. Now, if 90% of the data falls in this interval, we have to consider how much of the data falls outside of this confidence. Well, in this case, 0.9 minus 1, because we know that everything under the graph has to sum up to 1, means that I'm left with 0.1. Half of it is above, half of it is below. So this means that this interval right here is going to be 0.05. So then looking at my table, if I wanted to know what value has this amount of data below, I would need the value that has 0.9 plus 0.05 or 0.95 below that point. So we go to our Z table and we look within the table to find the closest probability we have to 0.95. So in that case, I come to right here. It falls directly between 0.9495 and 0.9505. meaning that because there's not one of them that is closer to than the other, I'm going to split the difference. So this would be 1.6, and then I come up here, it's between 4 and 5. So this means that my z value is going to be 1.645. This means that this negative z value is negative 1.645, because if it's zc and negative zc, they're the same value, just one's the positive, one's the negative. So in this case, we consider that our critical value, z critical, for c equals 0.9 is going to be 1.645. Let's do another example. Let's see what it would be if we had confidence level of 0.95. So in this case, we've got our normal distribution. We have our negative z critical. We have our positive z critical. And this accounts for 0.95 of the data. Now, if 0.95 of the data falls in this confidence interval, that means that 0.05 falls outside of it. Half of it's to the right, half it's to the left, meaning that I have 0.025 to the left of this. So if I look at what probability I would have to the left of this value, right, this is like our inverse probability, then it's 0.95 plus 0.025, or 0.975. So then I go into my table, I look for the value 0.975. So this is going to be right here. It's perfectly on the table, which means that it's going to be, I go to the left, 1.9, I go up to the top, 6. This means that my z value, where 0.975 is to the left of it, is going to be 1.96. And then the last one, we have a confidence interval of 0.99. So we get a negative z critical. We have a positive z critical. And we want 0.99 of the data to fall between these two z critical values. Well, if 0.99 falls between these two z values, that means only 0.01 can fall to the left and the right. Half it's left, half it's to the right. So this is going to be, so instead of 0.01, it's going to be 0.005, meaning that I need the value that has 0.995 to the left. Go to the table. I find 0.995, and it's going to be right here between 0.9949 and 0.9951. Now, the thing is, this is actually a value we use all the time. We actually know that it's closer to this one, even though our table rounds it the same. So it's actually going to be equal to z critical equals 2.58. And in fact, the table that we'll actually use going forward, I'll have a little subtable specifically for these three critical values. Let's do one more quick example that's not one of the three main ones that we use. Let's say that we have our standard normal distribution centered around 0. We have negative z critical. We have positive z critical. And let's say that 0.87 falls between these two critical values. So if 0.87 falls within this interval, that only leaves 0.13 to fall to the left and the right. Well, half of 0.13 would be 0.065. So then what I need to do is I need to figure out what z critical value would have 0.87 plus 0.065 to the left of it. So this ends up being 0.935. So again, going to my table, I'm going to look for the value that is closest to 0.935. So I go here and I get 0.9332 is the value below it. 0.9345 is the value above it. So it's closest to the value 0.9332. So this is going to be equal to 1.50. So my z critical is going to be 1.50. Now you might wonder, how does all this relate to what we're actually talking about? Because we wanted the confidence interval for mu, and all we're doing is we're saying what z critical values would give me this percentage of the data, or this decimal value of the data between them. Well, we're going to be doing like we did with the inverse normal, and we're going to be going from this standard normal to our actual normal based on our actual data. So that is the normal centered around the mean mu. And we're going to do this by looking at our transformation. Let's actually define what our confidence interval is, because we want to get it back to the space of the actual data. So for confidence level C, the critical value ZC is the number such that the area on our standard normal curve is between negative Z critical and positive Z critical. The area under this normal curve is the probability that the standard normal variable Z will be within that interval. That is to say that we have the probability that negative Z critical times our error, right? We have our standard error, which is going to be sigma over square root of n, is going to be less than or equal to, let's do less than, x bar minus mu is going to be less than Z critical sigma over square root of n. And then this whole probability is going to be equal to C. Now, what does this mean? Well, if you look at what this is, x bar minus mu, that's our margin of error that we talked about previously. It's the distance from our point estimate to the true parameter mu. And we're saying that we have some interval from negative Z critical times the scaling factor, right? The standard deviation divided by the square root of n, how big of a sample we have. That's getting us to our actual normal distribution. And it is between negative Z critical sigma over square root of n to positive Z critical sigma over square root of n. Now let's actually look at why this is true. Well, let's start with the fact that if we look at just this part, I'm actually going to rearrange it back to just the Z values. So we have negative Z critical is less than x bar minus mu divided by sigma divided by square root of n is less than positive Z critical, right? Because we know that if we have some Z value when we're using x bar, we can actually use the transformation x bar minus mu over sigma divided by square root of n. And we're saying that we know that this Z value should fall somewhere in that interval, this C amount of the time. So in this case, 0.87. And we'll be that amount confident that the true value would be in there. Because remember, we don't know what mu is, but we are, in this case, 87% confident that the true value would be somewhere in this interval. So now what we're going to do is we're going to solve for mu. So first thing I'm going to do is I'm going to multiply both sides, or all sides really, by sigma over square root of n. So this is going to be minus Z critical sigma over square root of n is less than x bar minus mu is less than Z critical sigma over square root of n. And now I need to get this mu by itself. So what I'm going to do now is I'm going to subtract x bar from both sides. So this is going to be minus x bar minus Z critical sigma over square root of n is less than negative mu is less than negative x bar plus Z critical sigma over square root of n. Now, I need to get mu by itself, not negative mu. So what I'm going to do is I'm going to multiply or divide everything by negative 1. So this is going to become positive x bar plus Z critical sigma over square root of n. Now, what happens with your sign whenever you multiply or divide by negative 1? It just flips. So this is going to become greater than negative mu times negative 1 becomes mu. This is also going to flip. X bar in this case becomes positive. This becomes minus Z critical sigma over square root of n. And then the last thing I'm going to do is I'm just going to flip this so it's in the form that we normally use. So doing that, this becomes x bar minus Z critical sigma over square root of n is less than or equal to mu is less than or equal to x bar plus Z critical sigma over square root of n. And this is how we find our confidence interval, which is just going to be the interval that we are some C amount confident that our true mean falls between. And the way that we can write this is our confidence interval can be written as an interval. So that's going to be, I'm going to just write it as our lower bound and our upper bound, which our lower bound is going to be this value here, x bar minus Z critical sigma over square root of n, up to x bar plus Z critical sigma over square root of n. So what this means is what we're saying is that our x bar is expected some C amount of the time to only deviate from the mean mu by plus or minus z critical sigma over square root of n. And this actually has a term. This is called our maximal margin of error. Our maximal margin of error is because what it's telling us is that our error is how far off our point estimate is from the true parameter. In this case, how far x bar is from mu. But we don't know what mu is. So what we're saying is, being some amount confident, the worst case scenario is that it should be within, negative z critical sigma over square root of n to positive z critical sigma over square root of n. So this is sort of a worst case scenario. So realistically, while my value might be here, what we're going to do is we're going to say, well, worst case scenario, I'm 87% sure that it's in here. Even though I might be closer, we're kind of taking the worst case scenario, which is why it's called the maximal margin of error. It's not just the margin of error, it's sort of the maximal margin of error to be this confident that my true mean falls within that interval. So let's talk a little bit more about that maximal margin of error. Since mu is unknown, our margin of error, which is x bar minus mu, and then we take the absolute value of that because we just want the magnitude, is also unknown. So what we're doing in this case is we're going to use the maximal margin of error, or sort of the worst case scenario margin of error, based on some level of confidence. And the way that we write this is we have E, which is our maximal margin of error, is equal to z critical sigma over square root of n. And this, again, E is called the maximal margin of error. Now, sometimes you may see places write this as ME for margin of error, something like that. So then our confidence interval is just going to be the probability that x bar minus E is less than mu is less than x bar plus E. And this is going to be equal to our confidence level C. This is our confidence interval right here. So our actual confidence interval is going to be written as the interval x bar minus E up to x bar plus E. So the last thing we're going to do before we end this video, and I'll do examples in the next one, is that I want to talk about the steps you take whenever you do a confidence interval. So the first step I would always do is write your given information. That is to say, whatever word problem you have or whatever information you have in a setup, write that down. This is going to be things like your sample size n, this is going to be your sigma if you have it, or your S if you don't have it. This is going to be your confidence level. It's going to be your X bar, things like this. Write them down as you read the problem and you get that information so you can determine what you need for this. The next step is you need to check your assumptions. Because first thing we need to do is we need to determine whether we can actually use a normal distribution to describe this. Remember, this is the case for when sigma is known. Well, that was one of our assumptions. Sigma is known. If sigma is not known, then the next assumption you have to check is n greater than or equal to 30? If sigma is known, you can use this for your finding your confidence interval. If sigma is unknown, but n is greater than or equal to 30, then you can use this method. If both fail, you will have to use a different method. Once you have this, set up your general form of your confidence interval. That is x bar minus E up to x bar plus E. From there, you need to figure out what is your maximal margin of error. So your E is going to be equal to z critical sigma over square root of n. Once you have your maximal margin of error, you're going to plug this back into your confidence interval. So this is going to give you your actual confidence interval. You're going to have numbers at this point, but pretty much your confidence interval at this point, you're going to be finding x bar minus z critical sigma over square root of n up to x bar plus z critical sigma over square root of n. You're going to find these values, and that's going to be your confidence interval. And then a lot of times we're going to ask you, how would you interpret this? And it would be something like, we are blank percent confident the true mean falls between blank and blank, where this value here is going to be whatever your C is, right? So I'm 87% confident, we're 90% confident, we're 99% confident that the true value falls between your lower bound. So in this case, it would be your lower bound. So you'd plug that number in, and then this one would be your upper bound. So for example, you might say, I'm 95% confident that the true mean falls somewhere between 5 and 15, something like that. Now, when you're actually doing one of these problems, generally when we interpret it, we do want to actually say what this true mean is or what it's about, right? You don't just usually say the true mean. You might say the true average weight of this, or the, true average height or amount of something, right? Say what this actually is whenever you're interpreting it. But this is basically the general form. Start by writing down your given information, right? Look at the word problem, determine what's given to you. Check all your assumptions. Is sigma known? If sigma's known, you can use Z. If sigma's unknown, but n is greater than or equal to 30, you can use Z. If both are true, you can use Z. The only time we're not going to be able to use Z is if both of these fail. If your assumptions pass, meaning one of these is true or both of them are true, then you can start with your general form of your confidence interval. That is to say, it is your point estimate of your mean mu, which is x bar, minus the maximal margin of error E, up to x bar plus E. Now, the reason I say write your general form is because even if your assumptions fail, this is still true. What's going to change is this, your maximal margin of error. So when you're using normal distribution, it is going to be Z critical sigma over square root of n. You then take that x bar, which is in your given information, you take that maximal margin of error, which you solved right here from the data in your given information, you're going to have actual numbers now. Plug those in, add them together, or subtract them, and you're going to get two numbers. Your confidence interval is between this value, your lower boundary, and this value, your upper boundary. And then we ask you to interpret the problem, and you would just say, I am C amount confident that the true mean falls between your lower value and your upper value. And that's it for the general idea for how to find a confidence interval for when sigma is known, and also for when sigma is unknown, but for when n is greater than or equal to 30. Thank you for watching. To continue learning, click the linked video here for the next lesson. If there's a topic you'd like me to cover, let me know in the comments. Don't forget to subscribe, and I'll see you in the next video.